I'm kind of waiting for everything to break now. But I think we're going to be okay. All right, so hi, welcome to Chip Decapping on a Budget. So if you don't know me, my name is Funsized, or Zach, and I've been hanging out with LayerOne crew for almost 10 years now, and been doing IoT Village, Tamper Evident Village, mostly bothering DG. So by day, I'm an electrical engineer, and by night, I'm a nerd. And so one of the things that I got really interested in about 9 months ago was how to decap ICs. So what is decapping? Integrated circuits are the black things that, well, usually black things that you see on PCBs. They're microcontrollers, op amps, all manner of embedded devices are almost always run out of these particular packages. And there's a long history associated with that, but modern chips are almost all silicon dies that are surrounded by protective material. The reason you want that protective material is to keep out dust and contaminants so that the silicon itself doesn't over-oxidize, to reduce vibration. So if you've got a part that's in an airplane or a car, then you want to make sure that none of your leads are going to come free inside of the part. And then you also want to keep it from visual observation so that it's harder for your other companies to reverse engineer the part. So why would we want to remove that encapsulation? Well, first of all, because it's fascinating. I was an electrical engineer working on some fairly complicated microcontrollers, and I just wanted to know what the insides looked like. Like any good hacker, I wanted to take it apart, right? I was just moving that scale down to a smaller piece. So the other reason that you might want to decap an IC is because so occasionally you'll get counterfeit. You want to make sure that the part that you're receiving really is the part that you paid for, especially in high regulatory environments like aircraft, automobile, DoD. All those industries are very sensitive to making sure that you have the right part and the QA involved with that. So where I work, we actually decap chips to make sure that they really are coming from the correct vendor. So then also, we could theoretically reverse engineer, and I'll get more into this later. That is not something that I personally have spent a lot of time exploring. It's a lot of resources, but we'll see that as we get towards the end. So real quick, what does the inside of an integrated circuit look like? So what we can visually see is this outer section is the black part that we can see. So these are the pins that would go down to our PCB. This particular component looks like a through-hole component. So if it was a surface mount, instead of the leads coming down, they would just be flat. But most of that in a modern process is not the actual integrated circuit. It's just the protection encapsulation material. So realistically, you have this very small silicon die in the middle, and that's where the actual circuitry is. And then it's bonded with these infinitesimally small wires out to the leads, and then all of that is protected with the encapsulation material. So what kind of things are encapsulants made out of? Encapsulants are usually, modern day, they're polymer epoxides. In order to increase durability and reduce cost, then they're filled with tiny particles of silica or sand. Sometimes they're ceramics. Sometimes they're silicone with an E. Every once in a while, especially in military applications, you'll see packaging that's metal. And then there's a whole class of sort of specialized packaging materials that are anti-tamper. So these are things that would not only reveal when you had messed with the chip, but would most likely destroy the contents of the die as you were trying to remove it. So what are ways that we can begin to get into actually removing this material? So the title of this talk is Chip Decapping on a Budget. So in a lot of the conversations that I've had over the past few months, people say, oh yeah, but what about, and those are all great suggestions, and I would love to hear those suggestions continue. But my budget for this was essentially, it wasn't quite zero because I definitely bought some stuff, but I wanted to see what is the cheapest way that I could do chip decapping, because in a theoretical chip decapping attack threat model, you assume that your opponent has a $10 million lab and a scanning electron microscope and a clean room, and nobody in this room has access to those, and none of you proved me wrong. Yeah. So what are ways that the average person can do chip decapping? And I didn't invent this. There's quite a few resources online of people having various success with various levels of methodology. So what I wanted to do was bring all of those methodologies kind of into a meta focus and give you guys an overview of here are all the different ways that you might be able to access this depending on what your interests are and what your cost levels are. So the first thing that we're going to look at is mechanical removal. And this is what most people think of first when they assume the tools that you're using. So they are like, okay, cool, I could just scrape it away with a file, or I could use sandpaper, and those things are true. Some people even use milling machines. Here's the problem. The rest of this talk is basically going to be trying to blow your minds with scale, because we're talking about things that are so infinitesimally small and so infinitesimally precise that it really pushes the boundaries of what humanity is capable of, let alone what we as individuals are capable of. So, for example, your standard milling machine is generally going to hold a tolerance, and this is like your average Bridgeport sitting in a garage. If it's a good one or a new one, is going to hold to about a thou tolerance, or 0.001 inches. That's 0.0254 millimeters. That's pretty small. On an item that you handle every day, you would be very hard pressed to notice a thou difference. But if you think about the scale at what we're talking, most modern processes are measured in the hundreds of nanometers. So we're talking 6 orders of magnitude between an IC surface and what the minimum tolerance of an average milling machine can hold. Yes, there are milling machines that can hold much more precise tolerances, but not 6 orders of magnitude more tolerance. So it's a little bit hard to use milling machines to get right down to the face of the IC. I said this in a talk about 6 months ago, and a gentleman in the crowd went out and proved me wrong. So he went home, he grabbed a bunch of his old SO8 IC dip package ICs, and he milled the top off of them, and he was able to observe the IC. And that's awesome. So it's totally doable with a milling machine. However, not for modern processes. The chip that he grabbed was manufactured, well, it was probably manufactured recently, but it was invented in the 80s. It was large feature sets. But there is still an advantage to mechanical material removal. What you might want to do is remove the bulk of that material before you use other methodologies to get down to the very top of the surface. So advantages to mechanical, commonly available tooling. Everybody's got a Bridgeport, right? Yeah. And there are no hazardous chemicals involved. And then, so the flip side of that is because they're commonly available, they tend to not be that precise. And you have to have a priori knowledge of the chip. You can't just start burrowing down into it and then stop when you think you've hit silicon. It doesn't work. Okay, so this is the one that everybody talks about. Chemical removal. So acids and laboratory equipment, I think is the mental picture that everyone has when you start talking about chip decapping. So the standard recipe for using fuming acids to remove material from an IC is 1 part sulfuric acid, 1 part nitric acid, and 3 parts sulfuric acid. And you bring that up to about 90 degrees C, so just below boiling, and you leave your IC in that mixture for between 30 and 45 minutes. Here's the problem. Because it's just below boiling and you've got these acid concentrations that are between 70 and 90%, the fumes that are coming off of it, it's steaming, right? The fumes that are coming off of it are highly caustic. They are so caustic that if you expose fabric to these fumes for long enough, they will spontaneously burst into flame. So that's bad. Yes. Well, so this is where I may or may not have been doing this in my apartment. And I may or may not have almost caught some things on fire. So then I realized that I needed a fume hood. So a fume hood is a device that allows you to work in a contained space, and it pulls enough air through the hood that essentially no fumes inside of that will be exposed to the outside, and then it goes through a filtration system. So just to give you an idea of the depths that I went to on this, I put together a couple of prototypes for homemade fume hoods. This is not my photo, by the way. This is just what it might look like if you are, so this is a hot plate, you've got your chip in a beaker with acid and it's decapping it. My picture went away. I'm sure I'll find it later. So with a fume hood, there's all these crazy calculations. You have to know how much air is basically falling on the surface of your fume hood. You have to be able to pull enough air with your fan consistently that none of those fumes escape. You have to make sure that all of the materials that are exposed to those fumes as it traverses and then exits whatever facility you're in aren't affected by the acid. So you have to have stuff that's either incredibly resilient to fuming or is a material that the sulfuric and nitric acids don't eat. And then after that, in order to not light your neighbors on fire, you have to then filter it. And so there are, for those of you who are interested, there are methodologies for building your own carbon filters. But then I remembered that I had no budget. So, all right, let's try something different. I threw this one in because everybody always asks. This is lasers. Yes, you can use lasers to decap. No, most people don't have access to a laser cutter at home. Quiet, Mr. Bot. So, and this, I think, is a reasonable avenue of pursuit because it's not that hard to get access to a laser cutter. So I'm sure there's stuff to explore here. I didn't have time to get to it. Advantages and disadvantages of a chemical removal. So I think I must have found my slide here. There it is. That's the fume hood chemical process. So then there's my method. So just a few science facts for you. Propane air mixtures burn at about 1100 degrees C. Epoxide materials, like those that encapsulation materials might be made out of, carbonize and fall apart much lower temperatures than that. But silicon melts at about 1414 C. So now we've got a really nice gradient. Oh, you've got to be flippin' kidding me. It's my photo. It's one of those days, guys. While this is downloading, I will continue. But this was my my demo. This is the demo portion. Right? Okay, so I'm sure those fumes aren't toxic. So you can see what's happening. So this is it's a PIC 16 microcontroller in a really old school dip package, and the hard epoxide is just coming off in huge chunks. And you can see inside of there's the copper heat transfer platter, which is a component of many ICs. And then there was an itty bitty tiny IC. So here's a picture of some of the ICs that I've decapped. The one that we're talking about is that guy. So that came out of that huge SOIC. It's maybe a 50th of the total volume. So these are a couple of pictures. These are the pictures that I snapped the third day that I tried this. So this was actually, so this is a special picture because it's an EEPROM. And so you can see here in the corners, it's still got its bond wires. The reason those are there is because I didn't actually use my method to decap this chip. It's got a window in it, so it's old enough that you could still use light to clear the EEPROM. And so I actually just took this photo under a microscope with my cell phone through the eyepiece. So it doesn't get much fucking cheaper than that. Another shot, honestly, I thought these were beautiful pictures. Other than the photographer quality, it's really interesting stuff. This is that PIC 16 that I decapped. So you can see some really interesting chromatic aberrations in here. And basically what's going on with those colors is on top of the silicon, you have different thicknesses of silicon dioxide, and that's from the manufacturing process. Sometimes it's on purpose, sometimes it's just an artifact left over. But because you have different thicknesses of the silicon dioxide, which is acting like a prism, you get different colors that splash through your chip. So this is not a colorized image. This is straight up out of the microscope from my cell phone. It does kind of look like SimCity. Okay, so does anyone know what year the first 10 micrometer process was developed? That's awesome. Totally not an audience plant. Okay, so real quick, we've just talked about how do you get these silicon dyes out of their encapsulation material. Now I want to talk a little bit about how to observe them and what you're seeing. So I initially had a really long, incredibly boring description of the manufacturing process for silicone wafers. The process itself isn't boring, but I still managed to make it snoozy. So what I would suggest is if you have no idea how silicon wafers are made, you should Google it. It is utterly fascinating. The process is incredible, and the steps that we go through to get to modern technology blow my freaking mind every time. But for today, let's stick with, we're gonna look at some pretty pictures, and we're gonna use some terminology that comes from the silicon world. So a wafer is the crystalline silicon structure that has been sliced really thinly that ICs are etched and doped onto. Doping is where we are impregnating those silicon crystals with different types of materials, and that's what turns them into transistors or logic gates or PN junctions. The die is after you've taken that wafer and you've done your process on it, you then slice it up into those tiny squares that we saw in the picture earlier. And then process is when someone's talking about the latest Intel process or the latest TSMC process, they're talking about the size of a single transistor gate. And that's XY dimensions generally described in micrometers or nanometers. So the young audience member was totally right. The first 10 micrometer process was developed in 1971. Then, as you can see from this slide, it gets increasingly smaller, and eventually we're going to get to 5 and maybe even 3 nanometer processes. They actually think we're starting to, at that point we're pushing up against the limits of what's possible with atoms. And so even though we have this roadmap for 2022, which is only 3 years away, isn't that weird? They're not really sure we're going to get to 3 nanometers. But there's something else here that's really critical. Notice that I have these grouped into 2 categories, optically observable and non-optically observable. Why is this important? So does anybody remember what the wavelength of light is, visible spectrum? 400 to what? 700 nanometers. So when you are observing something with light, you need that item to be at least half a wavelength of light large for the light to be able to interact with the material structure. So if you have a feature size that is smaller than the smallest wavelength of light by a factor of 2, not even an order of magnitude, you're not going to be able to see it. So that means that basically anything developed after 1997, we can't use microscopes to see anymore. Now we have to use scanning electron microscopes, confocal beams. I've even heard methodologies for things like focused ion beam reflectology. That is a whole nother talk. I was really having a hard time not just turning this into a microscopes talk, because microscopes are awesome. But fear not, so far, all of the chips that I have decapped have used processes that were still in the optical observability range. And I think the reason for this is pretty straightforward. The technology required to go to these really small processes is really only useful if you're coming out with the latest processor or the latest chip, right? So Intel microcontrollers, they may be repackaged, they may be refactored, but they're using transistor design from 20 years ago because I can see it, and that's how I know. Okay, so let's talk microscopes. Do you want to get digital or optical? Optical microscopes are, and by that I mean purely just lenses, reflecting light or directing light. You can also get digital microscopes. My experience so far with digital microscopes has been really not great. That doesn't mean that there aren't good digital microscopes out there, but they're not inexpensive. And I'm a cheap bastard. So I went with optical. So then the next question is swing, arm, or stand? And okay, now you're really getting into the grainy details there, Funsized. Why do we care about what holds the microscope? Well, it turns out that it's really flippin' important. And the reason it's really flippin' important is because when you're observing these incredibly infinitesimally small details, if your microscope isn't properly aligned, if your lenses aren't perfectly clear, there's all of these tiny little factors that come into play to make the image better or worse. And we're going to talk about ways that you can improve those. But then you need to know, okay, mechanically, is my lens aligned with my observation subject? And then the other really, really, really important thing is lighting. Because what's happening is, as you go down in scale, you're getting less and less photons that go back into your eye. And so, just from a statistical point of view, unless you put a shit ton of photons into your observation specimen, you're not going to be able to see it very well. And I'll have a photo later in the presentation of what my setup looks like. Okay, so we went over this already. Unless you're operating inside of the wavelength of visible light, you're not going to be able to see it. So the one thing that I wanted to touch on here in specific is the best way to improve your image quality. And frankly, this is a technique that I use for every debugging task in my life ever. Not microscopes, not electrical engineering, but everything. Which is, to improve quality, you pick the biggest error source and you kill it with fire, and then you move on to the next biggest error source and you kill it with fire. So I'm going to talk about the steps that I went through to kill all of my error sources. So let's just talk microscopes again for a second. The lens and lens focal point should be perfectly normal to face of die. So what this means is we're looking at features that are approximately 100 nanometers tall. If you're slightly out of focus, you're not going to be able to see that. Slightly out of focus in this case means essentially 0.01 degrees out of alignment. Incredibly small details. So you need some way to align your microscope so that it is perfectly friggin' flat. And then, like I said earlier, lens quality really matters. And this is where the cost goes up, right? So I'm using a microscope that I sourced from a secondhand dealer, and the microscope didn't fit in the stand that I had, and I have gone through, let me tell you, quite the journey to get this thing up and running. But what I learned a lot about on the way was all the little nicks and trannies. That is not what I was trying to say. Nooks and crannies. Man. Nooks and crannies into which you want to fit all these error sources. So, I said before, additional light is required at really high magnifications. The angle of light is really important. So, we were talking about the coloration on that earlier slide. The coloration comes from the thickness of that silicon dioxide. So as you are changing the angle of light, you are changing the prismatic effect that's being reflected back into the lens. So you can actually get really, really different and different features and different colors as you're moving that around. So whether you're doing this for learning or for art, it's super important to have control over the angle of your light sources. And then also calibration slides. So calibration slides are really freaking cool because it's a glass slide just like you used in biology class, and it's got this tiny dot on it. Until you zoom in on that dot, and it's a whole ruler. It's awesome. That makes me laugh every time. So this is my setup at home. You can see so this is a ring light, and those LEDs are facing down. And LEDs are actually a really important choice because they have a particular color spectrum and they don't get hot. So those are, you want the color spectrum that you can get from really carefully picked LEDs, and on top of that, you don't have to worry about setting your setup on fire because this stuff gets so close that it is essentially touching the material. So then after I've got my downward facing ring light, I have another ring light that faces inwards because what I found with the initial light that I had purchased from the manufacturer, it just wasn't putting enough photons bouncing back into the aperture. Okay, cool. So after I got that set up, what I should have done, actually, now that I think about it, is set up a series of photos where I show you them getting brighter and brighter over time. I didn't think about doing that because I was just frustrated and I was trying to get it working in the moment. But this other picture is just me showing off because I 3D printed a whole bunch of parts for my own microscope so that I could tram it in perfectly. I was using calibrated blocks of metal, 321 blocks, to make sure that the frame was perfectly aligned with my specimen. And then I was using levels to make sure that everything was, digital levels too, not just bubble levels, to make sure everything was trammed in perfectly solid. So, here's that calibration slide that I was talking about. So that one div dot that you see on the screen, to your eye, it really does just look like a printer dot. And then when you zoom in, it's got all these divisions. This particular one shows 0.01 millimeter, which is still 4 orders of magnitude larger than nanometers. So this is really good if you're looking at processes that are in the hundreds of micrometers. You can literally just slap this clear slide on top of your specimen and count. It's super cool. Okay, so the next step is I'm able to look through my microscope and see the specimen, but now I'd really like to record it. So you could do what I did initially and use your cell phone, but if you remember from that previous picture, there was a whole bunch of vignetting. There was that circular edge. That's because the eyepiece is not designed to take photos through. It's designed for your eyes to look through, and your eyes are round. Well, the camera senses are rectangular. So what you really want is you want a viewing window that is set up to match your camera sensor. So we're talking low budget here, right? And this, I guess, maybe pushes the boundaries of what really low budget would be considered, but I have a cheap DSLR. It's a low-end Canon body with, I think it was a $40 adapter lens that takes it from the Canon mount to 30 millimeters. 30 millimeters is the standard for microscope lenses. And I have a special microscope called a trinocular. And the trinocular has the 2 eyepieces, so it's, instead of being a binocular, it's got a third piece in the back. So you put your camera up there. Actually, we saw a picture of it, didn't we? This is a trinoc. So there's the two eyepieces, and there's the third for the camera. So while we're looking at this, this is a huge moment arm, right? So what you don't want is you don't want vibrations from when you're touching the camera or using the camera to introduce motion into your microscope so that you would become non-planar to your specimen. So DSLRs, because inherently they're not mirrorless, they have a prism in them that snaps out of the way when you take a photo. There's a tiny bit of shake. But you can actually set up almost all DSLRs with an anti-shake setting. If you dive down into your features, what it does is it snaps the prism out of the way, waits for a couple of microseconds, then takes the photo, then snaps the prism back. So the reason that's useful is because you're removing the vibration from the prism out of your image. The other thing that's really crucial is I use a remote trigger. So if you sit there and you press the button, you don't even have to worry about prism shake at that point. Just your finger press is an order of magnitude stronger than the forces from that prism shake. So everything's going to be vibrating. It's going to put your image out of focus. It's potentially going to move what you have focused on. So eliminating all those variables is coming back to killing that dragon one bite at a time, right? Another really important thing is stabilized power sources. So has anybody ever filmed like fluorescent lights or anything where it was, in the video, the footage, you could see it flashing? What's happening there is the camera is taking images fast enough that you're getting wave distortion from the AC signal coming in, because that's running at 50 hertz. And then, so not only does that produce bad video, but it can greatly interfere with how you're taking photos in the lab. So what you really want is you want a light source that is not in any way exposed to AC noise coming off the wall. That's a whole nother talk. That's an EE talk. And I'd be happy to give that one to you. In fact, I'm legally mandated to give you the ground safety rules at least once a week. So come see me afterwards and we'll get that taken care of. The other thing that I thought was really interesting was focus stacking. So sometimes when you're focusing on these really infinitesimally small bits, you can't actually see the entire feature. You're at such a high magnification that your focal plane is, let's say it's only 10 nanometers deep, and the features you're looking at are 100 nanometers deep. So now you can only get about a third of that feature in focus at a time. Well, through the magic of digital manipulation, if we mechanically move our focal plane down through those areas and take multiple images and then combine those back together, you can get an incredibly clear image. So biologists have been using this to get way better pictures of cells. And to my knowledge, I'm not aware of anybody using this technique for ICs other than myself. So it's pretty cool. I don't have any images to show you today because there's some tricks there where basically you have to be able to move your focal plane without touching the camera. So I'm going to have to automate some stuff. But that's, we're getting there. This is something that you could do in your mad scientist basement at home. The tools for focus stacking, there's 2 open source and free ones. And then if you have Photoshop, I think anything after CS6 has it baked in. You say, yes, focal stack, and it'll automatically figure out which images have the tightest focus and pull those bits out. So, great. Now we've figured out how to get into the chip, and we've figured out how to look at the chip and get really good images of the chip. Now what, Zach? Well, being able to interpret the processes that you see on the surface of the chip is somewhat challenging. There's 2 reasons for that. One is, so the type of engineer that builds these silicon dies is a VLSI engineer. So that's very large silicon integration processes. And if you are a VLSI engineer, please come talk to me. I would love to know more. My education, my formal education in electrical engineering covered VSLI very briefly, but it never went any further. And there's information online, but it hasn't been satisfactory yet. I've been able to get a couple people to ping me on Twitter with some information, and that was super helpful. It really opened the gateway in some areas, but almost all that stuff is trade secret protected, and I think that's the problem. Well, maybe problem is the wrong word, but that's why it's hard to find information, is that for the most part, these are proprietary techniques that nobody wants to talk about because that's what keeps them, putting food on the table. So, but the short version of how to interpret it is everything's a transistor. And specifically, everything's going to be some sort of FET, because FETs are really easy to manufacture. And so if you are looking at a large format die and you see a bunch of stuff, you're going to see a bunch of dots. And this is another one of those things that we don't have time for today. So I'm going to show you some pictures. I'm not going to get away without showing you some cool stuff, but I'm not going to go into how to interpret what a transistor looks like, because then we have to go into how a transistor is built, and it's a rabbit hole. It's a fucking awesome rabbit hole that you should totally go down, but it's a rabbit hole. So we're going to skip that today. Here is a chip. So I've got resources and sources for all of this stuff at the end of my talk, which I will make available, whether it's on my website or we'll push it out through the LayerOne website. So you can not only download this presentation, but all the links to all the resources that I have are in there. So one of the really cool resources is Zeptobars. So Zeptobars are, I believe they're Russian or Ukrainian dudes that do this for fun. And I don't know how they got funded, but they've got some really nice equipment. So basically what they do is they've got a XY table where they put the die on the XY table, and then they take a picture, and then they move it over, and they take a picture, and so they scan across this image. So this is probably 50 to 100 photos of this particular die that then they combine together using stitching tools in Photoshop. The reason that's really neat is because it gives you incredibly high resolution images. So if you wanted to notice here in the photo, there's what appears to be dust. It's like red and green dust. Those are all transistors. If you go on your home screen and you download the high-res image and you explode it out, you can actually see the pattern of the transistors. It's really cool. So I would totally recommend that. Zeptobars.com.org. The link is in the later slides. Okay, so let's just take a look real quick at what's going on here. These dots on the corners, on the sides, those are pads that they attach the bond wires to. So if you remember in earlier photos, there was those wires that were coming out of the dies, and those looked pretty small, right? But if you look at those in relation to the rest of the IC, that's the largest feature on this chip, are these big honkin' bond wire pads. So then in the upper right, whenever you see structures like this, it's almost always they're using that for their muxing. So if you've ever worked with chips where you've got a bunch of pins that have multiple functionalities, they have to have some way to route between those functionalities. And so when you're seeing those sorts of structures, you're getting your muxing in. I believe that this is the AT Tiny Micro. I was trying to pull up chips that I thought people might recognize. One of the only things about Zeptobars that is maybe disappointing would be one word, is that a lot of the chips they do are older Russian chips, which is fascinating, don't get me wrong, but it doesn't necessarily help me understand modern processes, right? But this is all the baked-in logic for their arithmetic logic unit. It's going to be how they're doing onboard register processing, all that kind of stuff. And then this is most likely, onboard EEPROM, onboard RAM. This is an ESP8086. And I think these are utterly fascinating. So heck if I know what these structures are. I mean, I'm pretty sure they're RF tuned inductors. Or resonators or oscillators, but that's friggin' cool. I mean, this is why I got into this, is because I find this stuff fascinating. And then I have, I don't know what all this stuff is. I want to learn more. So if you're a VLSI designer, come talk to me. This is a CMOS 555 timer. So if you've ever used a 555 timer and you got it in the old school dip package, you've got about 90% sand. I mean, okay, let's be clear. This is all sand because it's silicon, right? But you've got about 90% undoped sand. Earlier we were talking about counterfeiting. One of the things that Zeptobars does is whenever they find a counterfeit chip, they'll do a real fake comparison. And a lot of the times, the designers don't even take the time to copy the manufacturing notices. So, they'll get all of the circuitry right. It'll look slightly different. It's always worse quality. But there's even been some fakes where they went all the way to have the logos on the board reproduced. And the way that they figured out that these were counterfeit chips was they did analysis and they found out that the shaping of the letters was just different enough that they couldn't track between the two manufacturers. Frickin' awesome. What's next? So in order to get images like that, I need to get an XY table. That shouldn't be too terribly hard. You get a stepper motor, you use ball screws. This is a problem that I think is actually pretty easy to solve, and I think that totally falls under chip decapping on a budget. Also, I just need to get a motor for turning the focus on my camera when I'm not touching it, and I need to do something that's low vibe, so probably not a stepper. Higher quality microscope, both optics and frames. What I should have done was put together an Amazon wish list. If anyone wants to sponsor Funsized Industries, that would be fucking awesome. But I really don't, if you look at what I did, you can't go any cheaper. I really did bottom of the barrel, like college student poor, and I'm not, don't worry, but I went there because otherwise, how can everybody see the really cool optics stuff that I did? So I used a cheap microscope, I have a cheap frame with a cheap camera and a cheap lens. So if you want to do better, get a high quality microscope. I've been looking at biotech auctions to find really high quality Nikon microscopes for 1/10 of the price of what they would cost new. So look for auctions from startups, especially biotech startups. For fume hoods, there's plans in the links for how to make your own. Please don't kill yourself. And then the laser etcher, I think that if you have the ability to do an XY table, you probably have the ability to do a laser etcher. I know that almost every hackerspace has a laser cutter. And if they're willing to risk you fouling their laser cutter with your IC experiments, that's awesome, and I want to see photos. What else is next? So if you had an idea while you were watching this, yeah, okay, but Funsized, why didn't you try? Please come talk to me. This has been an experiment. It's been a really fun ride, and I've got a heck of a time out of it. So I plan on doing more. I plan on improving this. But now you too, for $0, can go look at ICs. One quick personal plug. I'm one of the organizers of another conference in October called ShellCon. It's about the same size. It's in San Pedro. I think it's a really fun con, and I would love it if you guys came. Our CFP just opened up, and it's open through July 20th. So please submit. We want to see some cool talks. I would love it if somebody submitted some chip decapping talks of here's how I did better than Funsized, because it's not hard. So ShellCon, October 11th and 12th, and we'll be doing pre-reg and ticket sales soon. If you want to get a hold of me, you can email me at funsized@shellcon.io, or you can hit me up on Twitter at ZJPoly, or if you want to see the terrible code that I've written for all of this, you can go to my GitHub. At ZJPoly is also my Instagram, which is almost no dye shots and almost all food shots. So I know some of you are already going there. And this is the resources. So like I said, I will make this available online. I've got about 10 minutes here. Are there any questions, ideas, comments, complaints, tomatoes? I know a guy. No, okay, so true story, it's not that hard to buy 70% nitric acid, which is terrifying because it's used in creating really gnarly things. But I guess they assume that if you're much more likely to light your apartment on fire than you are to make RDX. So Grainger sells 60% nitric acid. They actually sell 90% nitric acid, but I think you have to have a business license to buy that. But you can just buy regular 60% nitric acid and sulfuric acid from Grainger. And then the trick is the way that they go from 60% to 90% is they boil off the water. We're already boiling acid. So if you're set up to do that, you can take your own concentrations up to 90. Please don't kill yourself. Cannibal. So I cheated because I got the microscope for free. I already had the camera. So I spent $50 on the lens. I already had a blowtorch. The calibration slide was 20 bucks on Amazon, so that's 70 bucks. The ICs I pulled off of old electronics that I had lying around. By the way, okay, so I did a really dumb thing. I told people that if they had old electronics that they wanted me to decap, that they should give it to me. That was a huge mistake. I now run my very own electronics e-waste shop. I have piles and piles of old electronics. I don't want them. Do not bring them to me. So yeah, that's like 70 bucks. A nice new low-end microscope is about $600. The camera body that I'm using is about $300. I think that's it. My microscope goes from 4x to 290x. I'm sorry, 270x. So the way that that works is you've essentially got 3 areas on most inspection microscopes. That is something I forgot to mention. Inspection microscopes versus biology microscopes. So biology microscopes light the specimen from underneath, but since silicon dyes are opaque, this does you diddly shit. So make sure you get an inspection microscope where it's designed to light it from the top. So I've got an AM scope. I'm not endorsing them necessarily, but so far it's been pretty good quality. I like it. You've got your eyepieces, and eyepieces generally come in 10, 20, and 30x. Then you've got your objective lenses, and your objective lenses are they're essentially the tubes that stick down right over the top of your specimen. And my objective lenses are vary from 0.7 to 4.5. It's got a zoom functionality. And then there's another lens, which I can never remember the name of. It begins with a B. Somebody help me out. Barlow lens. So the Barlow lens screws onto the underside under the objective lenses, and that's either a 0.5 lens or a 2x lens. So on my microscope, because I'm trying to see these really small features, I've got a 2x Barlow lens, and then I can take it up to a 4.5 objective lens magnification, and then I've got 30x eyepieces. So 30 times 2 times 4.5 is my max magnification, so approximately 270. So those are both interesting ideas. The question was, have you ever thought of using oil immersion lenses or UV light? So UV light would work because you're getting your wavelength smaller, so that's good. It's higher frequency. What I don't know is how you would image it then. I guess actually most camera sensors can see UV. So that is interesting. I really like that. If you've ever used a commercial like DSLR, or oftentimes there's a film in front of the sensor that filters out UV light. And that's primarily because humans' eyes can't see it, and so there's a difference between what your eyes saw and what you actually ended up taking with the camera. So there are guys that do UV conversions on their cameras where they take that filter off and actually put up a visible light filter so that all that's coming into the camera is UV light, and it's really cool. So that's an excellent idea, and the oil immersion is also a really good one. More expensive, for sure. If anybody has a confocal microscope that they want to let me borrow, come talk to me. The question was, have you ever shipped out a chip to a third party to do decapping? You know, one of those labs that is equipped to do it really well, and compared it to your stuff? And the answer is no, I haven't. Mostly because that costs money, and it's over my budget. Do you know approximately how much that might run? Okay. So the response was that it's a couple $100 to get a chip decapped. So that'd be very interesting. I would like to try that. Other questions? I've got about 3 minutes.
One option you might consider Funsized they do, but it might be to find a surplus of glove box. You purge out the nitrogen, so this is always applied as nitrogen. Purge out the nitrogen, and that won't be setting anything on fire.
That's an excellent suggestion, thank you. So the comment was that if you're looking to build a cheap fume hood, use an old glove box and then purge it with nitrogen. Who doesn't want to purge stuff with nitrogen? I get excited every time I say that. See previous conversations about fuming acid. All right, guys. Well, I think I'm out of time. Thank you for being a wonderful audience, and we'll talk to you later.